A fuel cell is a device that converts the chemical energy from a fuel into electricity through a chemical reaction with oxygen or another oxidizing agent. Hydrogen produced from the steam methane reforming of natural gas is the most common fuel, but for greater efficiency hydrocarbons can be used directly, such as natural gas and alcohols like methanol. Fuel cells are different from batteries in that they require a continuous source of fuel and oxygen air to sustain the chemical reaction, whereas in a battery the chemicals present in the battery react with each other to generate an electromotive force. Fuel cells can produce electricity continuously for as long as these inputs are supplied. The first fuel cells were invented in 1838. The first commercial use of fuel cells came more than a century later in NASA space programs to generate power for probes, satellites and space capsules. Since then, fuel cells have been used in many other applications. Fuel cells are used for primary and backup power for commercial, industrial and residential buildings and in remote or inaccessible areas. They are also used to power fuel cell vehicles, including forklifts, automobiles, buses, boats, motorcycles and submarines. There are many types of fuel cells, but they all consist of an anode, a cathode and an electrolyte that allows charges to move between the two sides of the fuel cell. Electrons are drawn from the anode to the cathode through an external circuit, producing direct current electricity. As the main difference among fuel cell types is the electrolyte, fuel cells are classified by the type of electrolyte they use, followed by the difference in startup time ranging from 1 second for PEMFC to 10 minutes for SOFC. Fuel cells come in a variety of sizes. Individual fuel cells produce relatively small electrical potentials, about 0.7 volts, so cells are stacked, or placed in series, to increase the voltage and meet an application's requirements. In addition to electricity, fuel cells produce water, heat and, depending on the fuel source, very small amounts of nitrogen dioxide and other emissions. The energy efficiency of a fuel cell is generally between 40–60%, or up to 85% efficient in cogeneration if waste heat is captured for use. The fuel cell markets is growing, and Pike Research has estimated that the stationary fuel cell market will reach 50 GW by 2020. History. The first references to hydrogen fuel cells appeared in 1838. In a letter dated October 1838 but published in the December 1838 edition of the London and Edinburgh Philosophical Magazine and Journal of Science, Welsh physicist and barrister William Grove wrote about the development of his first crude fuel cells. He used a combination of sheet iron, copper and porcelain plates, and a solution of sulfate of copper and dilute acid. In a letter to the same publication written in December 1838 but published in June 1839, German physicist Christian Friedrich Schaparagraph discussed the first crude fuel cell that he had invented. His letter discussed current generated from hydrogen and oxygen dissolved in water. Grove later sketched his design, in 1842, in the same journal. The fuel cell he made used similar materials to today's phosphoric acid fuel cell. In 1939, British engineer Francis Thomas Bacon successfully developed a 5 kW stationary fuel cell. In 1955, W. Thomas Grubb, a chemist working for the General Electric Company, further modified the original fuel cell design by using a sulfonated polystyrene ion exchange membrane as the electrolyte. 3 years later another GE chemist, Leonard Nedrach, devised a way of depositing platinum onto the membrane, which served as catalyst for the necessary hydrogen oxidation and oxygen reduction reactions. This became known as the Grubb-Nedrach fuel cell. GE went on to develop this technology with NASA and McDonnell aircraft, leading to its use during Project Gemini. This was the first commercial use of a fuel cell. In 1959, a team led by Harry Orig built a 15 kW fuel cell tractor for Alice Chalmers, which was demonstrated across the U.S. at state fairs. This system used potassium hydroxide as the electrolyte and compressed hydrogen and oxygen as the reactants. Later in 1959, Bacon and his colleagues demonstrated a practical 5 kW unit capable of powering a welding machine. In the 1960s, Pratt & Whitney licensed Bacon's U.S. patents for use in the U.S. space program to supply electricity and drinking water. In 1991, the first hydrogen fuel cell automobile was developed by Roger Billings. UTC Power was the first company to manufacture and commercialize a large, stationary fuel cell system for use as a cogeneration power plant in hospitals, universities and large office buildings. UTC Power continues to be the sole supplier of fuel cells to NASA for use in space vehicles, having supplied fuel cells for the Apollo missions and the Space Shuttle program, and is developing fuel cells for cell phone towers and other applications. Types of fuel cells. Design. Fuel cells come in many varieties. However, they all work in the same general manner. They are made up of three adjacent segments, the anode, the electrolyte, and the cathode. Two chemical reactions occur at the interfaces of the three different segments. The net result of the two reactions is that fuel is consumed, water or carbon dioxide is created, and an electric current is created, which can be used to power electrical devices, normally referred to as the load. At the anode, a catalyst oxidizes the fuel, usually hydrogen, turning the fuel into a positively charged ion and a negatively charged electron. The electrolyte is a substance specifically designed so ions can pass through it, but the electrons cannot. The freed electrons travel through a wire creating the electric current. The ions travel through the electrolyte to the cathode. Once reaching the cathode, the ions are reunited with the electrons and the two react with a third chemical, usually oxygen, to create water or carbon dioxide. The most important design features in a fuel cell are the electrolyte substance. The electrolyte substance usually defines the type of fuel cell. The fuel that is used. The most common fuel is hydrogen. The anode catalyst breaks down the fuel into electrons and ions. The anode catalyst is usually made up of very fine platinum powder. The cathode catalyst turns the ions into the waste chemicals like water or carbon dioxide. The cathode catalyst is often made up of nickel, but it can also be a nanomaterial-based catalyst. A typical fuel cell produces a voltage from 0.6 V to 0.7 V at full rated load. Voltage decreases as current increases, due to several factors: activation loss, ohmic loss, mass transport loss. To deliver the desired amount of energy, the fuel cells can be combined in series to yield higher voltage, and in parallel to allow a higher current to be supplied. Such a design is called a fuel cell stack. The cell surface area can also be increased, to allow higher current from each cell. Within the stack, reactant gases must be distributed uniformly over each of the cells to maximize the power output. Proton exchange membrane fuel cells. In the archetypical hydrogen-oxide proton exchange membrane fuel cell design, a proton-conducting polymer membrane separates the anode and cathode sides. This was called a solid polymer electrolyte fuel cell in the early 1970s, before the proton exchange mechanism was well understood. On the anode side, hydrogen diffuses to the anode catalyst where it later dissociates into protons and electrons. These protons often react with oxidants, causing them to become what are commonly referred to as multi-facilitated proton membranes. The protons are conducted through the membrane to the cathode, but the electrons are forced to travel in an external circuit because the membrane is electrically insulating. On the cathode catalyst, oxygen molecules react with the electrons and protons to form water. In addition to this pure hydrogen type, there are hydrocarbon fuels for fuel cells, including diesel, methanol and chemical hydrides. The waste products with these types of fuel are carbon dioxide and water. When hydrogen is used, the CO2 is released when methane from natural gas is combined with steam in a process called steam methane reforming to produce the hydrogen. This can take place in a different location to the fuel cell, potentially allowing the hydrogen fuel cell to be used indoors, for example in forklifts. The different components of a PEMFC are bipolar plates, electrodes, catalyst, membrane, and the necessary hardware. The materials used for different parts of the fuel cells differ by type. The bipolar plates may be made of different types of materials, such as metal, coated metal, graphite, flexible graphite, Ca-C composite, Carbona-polymer composites etc. The membrane electrode assembly is referred as the heart of the PEMFC and is usually made of a proton exchange membrane sandwiched between two catalyst-coated carbon papers. Platinum and or similar type of noble metals are usually used as the catalyst for PEMFC. The electrolyte could be a polymer membrane. Proton exchange membrane fuel cell design issues, costs. In 2013, the Department of Energy estimated that 80 kilowatt automotive fuel cell system costs of $67 per kilowatt could be achieved, assuming volume production of 100,000 automotive units per year, and $55 per kilowatt could be achieved, assuming volume production of 500,000 units per year. In 2008, Professor Jeremy P. Mayers estimated that cost reductions over a production ramp-up period will take about 20 years after fuel cell cars are introduced before they will be able to compete commercially with current market technologies, including gasoline internal combustion engines. Many companies are working on techniques to reduce cost in a variety of ways, including reducing the amount of platinum needed in each individual cell. Ballard Power Systems has experimented with a catalyst enhanced with carbon silk, which allows a 30% reduction in platinum usage without reduction in performance. Monash University, Melbourne uses PEDOT as a cathode. A 2011 published study documented the first metal-free electrocatalyst using relatively inexpensive doped carbon nanotubes, which are less than 1% the cost of platinum and are of equal or superior performance. Water and air management. In this type of fuel cell, the membrane must be hydrated, requiring water to be evaporated at precisely the same rate that it is produced. If water is evaporated too quickly, the membrane dries, resistance across it increases, and eventually it will crack, creating a gas short circuit, where hydrogen and oxygen combine directly, generating heat that will damage the fuel cell. If the water is evaporated too slowly, the electrodes will flood, preventing the reactants from reaching the catalyst and stopping the reaction. Methods to manage water in cells are being developed, like electroosmotic pumps focusing on flow control. Just as in a combustion engine, a steady ratio between the reactant and oxygen is necessary to keep the fuel cell operating efficiently. Temperature management. The same temperature must be maintained throughout the cell in order to prevent destruction of the cell through thermal loading. This is particularly challenging as the 2 hours 2 plus O2 2 hours 2O reaction is highly exothermic, so a large quantity of heat is generated within the fuel cell. Durability, service life, and special requirements for some type of cells. Stationary fuel cell applications typically require more than 40,000 hours of reliable operation at a temperature of 35 °C to 40 °C, while automotive fuel cells require a 5,000-hour lifespan, under extreme temperatures. Current service life is 7,300 hours under cycling conditions. Automotive engines must also be able to start reliably at 30 °C and have a high power-to-volume ratio. Limited carbon monoxide tolerance of some cathodes. Phosphoric acid fuel cell. Phosphoric acid fuel cells were first designed and introduced in 1961 by G. V. Elmore and H. A. Tanner. In these cells, phosphoric acid is used as a non-conductive electrolyte to pass positive hydrogen ions from the anode to the cathode. These cells commonly work in temperatures of 150 to 200 degrees Celsius. This high temperature will cause heat and energy loss if the heat is not removed and used properly. This heat can be used to produce steam for air conditioning systems or any other thermal energy-consuming system. Using this heat in cogeneration can enhance the efficiency of phosphoric acid fuel cells from 50% to about 80%. Phosphoric acid, the electrolyte used in PAFCs, is a non-conductive liquid acid which forces electrons to travel from anode to cathode through an external electrical circuit. Since the hydrogen ion production rate on the anode is small, platinum is used as catalyst to increase this ionization rate. A key disadvantage of these cells is the use of an acidic electrolyte. This increases the corrosion or oxidation of components exposed to phosphoric acid. High-temperature fuel cells, SOFC. Solid oxide fuel cells use a solid material, most commonly a ceramic material called yttria-stabilized zirconia, as the electrolyte. Because SOFCs are made entirely of solid materials, they are not limited to the flat plane configuration of other types of fuel cells and are often designed as rolled tubes. They require high operating temperatures and can be run on a variety of fuels including natural gas. SOFCs are unique in that negatively charged oxygen ions travel from the cathode to the anode instead of positively charged hydrogen ions traveling from the anode to the cathode, as is the case in all other types of fuel cells. Oxygen gas is fed through the cathode, where it absorbs electrons to create oxygen ions. The oxygen ions then travel through the electrolyte to react with hydrogen gas at the anode. The reaction at the anode produces electricity and water as byproducts. Carbon dioxide may also be a byproduct depending on the fuel, but the carbon emissions from an SOFC system are less than those from a fossil fuel combustion plant. The chemical reactions for the SOFC system can be expressed as follows: anode reaction, 2H2 plus 2O2A 2 hours 2O plus 4A, cathode reaction, O2 plus 4A euro a 2O2A. Overall cell reaction, 2H2 plus O2 a 2 hours 2O, SOFC systems can run on fuels other than pure hydrogen gas. However, since hydrogen is necessary for the reactions listed above, the fuel selected must contain hydrogen atoms. For the fuel cell to operate, the fuel must be converted into pure hydrogen gas. SOFCs are capable of internally reforming light hydrocarbons such as methane, propane and butane. These fuel cells are at an early stage of development. Challenges exist in SOFC systems due to their high operating temperatures. One such challenge is the potential for carbon dust to build up on the anode, which slows down the internal reforming process. Research to address this carbon coking issue at the University of Pennsylvania has shown that the use of copper-based cermet can reduce coking and the loss of performance. Another disadvantage of SOFC systems is slow startup time, making SOFCs less useful for mobile applications. Despite these disadvantages, a high operating temperature provides an advantage by removing the need for a precious metal catalyst like platinum, thereby reducing cost. Additionally, waste heat from SOFC systems may be captured and reused, increasing the theoretical overall efficiency to as high as 80% to Euro 85%. The high operating temperature is largely due to the physical properties of the YSZ electrolyte. As temperature decreases, so does the ionic conductivity of YSZ. Therefore, to obtain optimum performance of the fuel cell, a high operating temperature is required. According to their website, Series Power, a UK SOFC fuel cell manufacturer, has developed a method of reducing the operating temperature of their SOFC system to 500 Euro 600 degrees Celsius. They replace the commonly used YSZ electrolyte with a CGO electrolyte. The lower operating temperature allows them to use stainless steel instead of ceramic as the cell substrate, which reduces cost and startup time of the system. MCFC. Molten carbonate fuel cells require a high operating temperature, 650 AA degrees Celsius, similar to SOFCs. MCFCs use lithium potassium carbonate salt as an electrolyte, and this salt liquefies at high temperatures, allowing for the movement of charge within the cell, in this case, negative carbonate ions. Like SOFCs, MCFCs are capable of converting fossil fuel to a hydrogen-rich gas in the anode, eliminating the need to produce hydrogen externally. The reforming process creates CO2 emissions. MCFC-compatible fuels include natural gas, biogas and gas produced from coal. The hydrogen in the gas reacts with carbonate ions from the electrolyte to produce water, carbon dioxide, electrons and small amounts of other chemicals. The electrons travel through an external circuit creating electricity and return to the cathode. There, Oxygen from the air and carbon dioxide recycled from the anode react with the electrons to form carbonate ions that replenish the electrolyte, completing the circuit. The chemical reactions for an MCFC system can be expressed as follows: anode reaction, CO32A plus H2O plus CO2 plus 2A, cathode reaction, CO2 plus a 1/2 O2 plus 2A CO32A, overall cell reaction, H2 plus a 1/2 O2 H2O. As with SOFCs, MCFC disadvantages include slow startup times because of their high operating temperature. This makes MCFC systems not suitable for mobile applications, and this technology will most likely be used for stationary fuel cell purposes. The main challenge of MCFC technology is the cell's short lifespan. The high temperature and carbonate electrolyte led to corrosion of the anode and cathode. These factors accelerate the degradation of MCFC components, decreasing the durability and cell life. Researchers are addressing this problem by exploring corrosion-resistant materials for components as well as fuel cell designs that may increase cell life without decreasing performance. MCFCs hold several advantages over other fuel cell technologies, including their resistance to impurities. They are not prone to carbon coking, which refers to carbon buildup on the anode that results in reduced performance by slowing down the internal fuel reforming process. Therefore, carbon-rich fuels like gases made from coal are compatible with the system. The Department of Energy claims that coal, itself, might even be a fuel option in the future, assuming the system can be made resistant to impurities such as sulfur and particulates that result from converting coal into hydrogen. MCFCs also have relatively high efficiencies. They can reach a fuel-to-electricity efficiency of 50%, considerably higher than the 42% efficiency of a phosphoric acid fuel cell plant. Efficiencies can be as high as 65% when the fuel cell is paired with a turbine, and 85% if heat is captured and used in a combined heat and power system. Fuel Cell Energy, a Connecticut-based fuel cell manufacturer, develops and sells MCFC fuel cells. The company says that their MCFC products range from 300 a kilowatt to 2.8 MW systems that achieve 47% electrical efficiency and can utilize CHP technology to obtain higher overall efficiencies. One product, the DFCERG, is combined with a gas turbine and, according to the company, it achieves an electrical efficiency of 65%. Comparison of fuel cell types. Efficiency of leading fuel cell types. Glossary of terms in table. Anode, the electrode at which oxidation takes place. For fuel cells and other galvanic cells, the anode is the negative terminal. For electrolytic cells, the anode is the positive terminal. Aqueous solution, AV, relating to, or resembling water bar made from, with, or by water. Catalyst, a chemical substance that increases the rate of a reaction without being consumed. After the reaction, it can potentially be recovered from the reaction mixture and is chemically unchanged. The catalyst lowers the activation energy required, allowing the reaction to proceed more quickly or at a lower temperature. In a fuel cell, the catalyst facilitates the reaction of oxygen and hydrogen. It is usually made of platinum powder very thinly coated onto carbon paper or cloth. The catalyst is rough and porous so the maximum surface area of the platinum can be exposed to the hydrogen or oxygen. The platinum-coated side of the catalyst faces the membrane in the fuel cell. Cathode, the electrode at which reduction occurs. For fuel cells and other galvanic cells, the cathode is the positive terminal. For electrolytic cells, the cathode is the negative terminal. Electrolyte, a substance that conducts charged ions from one electrode to the other in a fuel cell, battery, or electrolyzer. Fuel cell stack, individual fuel cells connected in a series. Fuel cells are stacked to increase voltage. Matrix, something within or from which something else originates, develops, or takes form. Membrane, the separating layer in a fuel cell that acts as electrolyte as well as a barrier film separating the gases in the anode and cathode compartments of the fuel cell. Molten carbonate fuel cell, a type of fuel cell that contains a molten carbonate electrolyte. Carbonate ions are transported from the cathode to the anode. Operating temperatures are typically near 650 °C. Phosphoric acid fuel cell, a type of fuel cell in which the electrolyte consists of concentrated phosphoric acid. Protons are transported from the anode to the cathode. The operating temperature range is generally 160 220 °C. Polymer electrolyte membrane, a fuel cell incorporating a solid polymer membrane used as its electrolyte. Protons are transported from the anode to the cathode. The operating temperature range is generally 60 100 °C. Solid oxide fuel cell, a type of fuel cell in which the electrolyte is a solid, non-porous metal oxide, typically zirconium oxide treated with Y2O3, and O2A is transported from the cathode to the anode. Any company in the reformate gas is oxidized to CO2 at the anode. Temperatures of operation are typically 800 to 1000 °C. Solution: A. An act or the process by which a solid, liquid, or gaseous substance is homogeneously mixed with a liquid or sometimes a gas or solid, bar homogeneous mixture formed by this process. Especially a single-phase liquid system, the condition of being dissolved. For more information see Glossary of fuel cell terms. Theoretical maximum efficiency. The energy efficiency of a system or device that converts energy is measured by the ratio of the amount of useful energy put out by the system to the total amount of energy that is put in, or by useful output energy as a percentage of the total input energy. In the case of fuel cells, useful output energy is measured in electrical energy produced by the system. Input energy is the energy stored in the fuel. According to the U.S. Department of Energy, fuel cells are generally between 40 to 60% energy efficient. This is higher than some other systems for energy generation. For example, the typical internal combustion engine of a car is about 25% energy efficient. In combined heat and power systems, the heat produced by the fuel cell is captured and put to use, increasing the efficiency of the system to up to 85 to 90%. The theoretical maximum efficiency of any type of power generation system is never reached in practice, and it does not consider other steps in power generation, such as production, transportation and storage of fuel and conversion of the electricity into mechanical power. However, this calculation allows the comparison of different types of power generation. The maximum theoretical energy efficiency of a fuel cell is 83%, operating at low power density and using pure hydrogen and oxygen as reactants according to the World Energy Council. This compares with a maximum theoretical efficiency of 58% for internal combustion engines. While these efficiencies are not approached in most real-world applications, high-temperature fuel cells can theoretically be combined with gas turbines to allow stationary fuel cells to come closer to the theoretical limit. A gas turbine would capture heat from the fuel cell and turn it into mechanical energy to increase the fuel cell's operational efficiency. This solution has been predicted to increase total efficiency to as much as 70%. In practice, the tank-to-wheel efficiency of a fuel cell vehicle is greater than 45% at low loads and shows average values of about 36% when a driving cycle like the NEDC is used as test procedure. The comparable NEDC value for a diesel vehicle is 22%. In 2008, Honda released a demonstration fuel cell electric vehicle with fuel stack claiming a 60% tank-to-wheel efficiency. It is also important to take losses due to fuel production, transportation, and storage into account. Fuel cell vehicles running on compressed hydrogen may have a power plant-to-wheel efficiency of 22% if the hydrogen is stored as high-pressure gas, and 17% if it is stored as liquid hydrogen. Fuel cells cannot store energy like a battery, except as hydrogen, but in some applications, such as standalone power plants based on discontinuous sources such as solar or wind power, they are combined with electrolyzers and storage systems to form an energy storage system. Most hydrogen, however, is produced by steam methane reforming, and so most hydrogen production emits carbon dioxide. The overall efficiency of such plants, using pure hydrogen and pure oxygen, can be from 35 up to 50%, depending on gas density and other conditions. While a much cheaper lead-acid battery might return about 90%, the electrolyzer fuel cell system can store indefinite quantities of hydrogen, and is therefore better suited for long-term storage. Solid oxide fuel cells produce exothermic heat from the recombination of the oxygen and hydrogen. The ceramic can run as hot as 800 degrees Celsius. This heat can be captured and used to heat water in a micro-combined heat and power application. When the heat is captured, total efficiency can reach 80–90% at the unit, but does not consider production and distribution losses. CHP units are being developed today for the European home market. Professor Jeremy P. Meyers, in the Electrochemical Society Journal Interface in 2008, wrote, "While fuel cells are efficient relative to combustion engines, they are not as efficient as batteries, due primarily to the inefficiency of the oxygen reduction reaction, They make the most sense for operation disconnected from the grid, or when fuel can be provided continuously. For applications that require frequent and relatively rapid startups, where zero emissions are a requirement, as in enclosed spaces such as warehouses, and where hydrogen is considered an acceptable reactant, a PEM fuel cell is becoming an increasingly attractive choice, if exchanging batteries is inconvenient." In 2013, military organizations are evaluating fuel cells to significantly reduce the battery weight carried by soldiers. Applications: power. Stationary fuel cells are used for commercial, industrial and residential primary and backup power generation. Fuel cells are very useful as power sources in remote locations, such as spacecraft, remote weather stations, large parks, communications centers, rural locations including research stations, and in certain military applications. A fuel cell system running on hydrogen can be compact and lightweight, and have no major moving parts. Because fuel cells have no moving parts and do not involve combustion, in ideal conditions they can achieve up to 99.9999% reliability. This equates to less than 1 minute of downtime in a 6-year period. Since fuel cell electrolyzer systems do not store fuel in themselves, but rather rely on external storage units, they can be successfully applied in large-scale energy storage, rural areas being one example. There are many different types of stationary fuel cells, so efficiencies vary, but most are between 40% and 60% energy efficient. However, when the fuel cell's waste heat is used to heat a building in a cogeneration system, this efficiency can increase to 85%. This is significantly more efficient than traditional coal power plants, which are only about 1/3 energy efficient. Assuming production at scale, fuel cells could save €20–40% on energy costs when used in cogeneration systems. Fuel cells are also much cleaner than traditional power generation. A fuel cell power plant using natural gas as a hydrogen source would create less than 1 ounce of pollution, other than CO2, for every 1,000 kWh produced, compared to 25 pounds of pollutants generated by conventional combustion systems. Fuel cells also produce 97% less nitrogen oxide emissions than conventional coal-fired power plants. One such pilot program is operating on Stewart Island in Washington state. There, the Stewart Island Energy Initiative has built a complete, closed-loop system. Solar panels power an electrolyzer, which makes hydrogen. The hydrogen is stored in a 500 US gallon tank at 200 pounds per square inch, and runs a Relion fuel cell to provide full electric backup to the off-the-grid residents. Another closed system loop was unveiled in late 2011 in Hempstead, NY. Fuel cells can be used with low-quality gas from landfills or wastewater treatment plants to generate power and lower methane emissions. A 2.8 MW fuel cell plant in California is said to be the largest of the type. Cogeneration, combined heat and power fuel cell systems, including micro-combined heat and power systems, are used to generate both electricity and heat for homes, office building and factories. The system generates constant electric power, and at the same time produces hot air and water from the waste heat. As the result, CHP systems have the potential to save primary energy as they can make use of waste heat, which is generally rejected by thermal energy conversion systems. A typical capacity range of home fuel cell is 1 euro 3 kW/4 euro 8 kWth. CHP systems linked to absorption chillers use their waste heat for refrigeration. The waste heat from fuel cells can be diverted during the summer directly into the ground, providing further cooling, while the waste heat during winter can be pumped directly into the building. The University of Minnesota owns the patent rights to this type of system. Cogeneration systems can reach 85% efficiency. Phosphoric acid fuel cells comprise the largest segment of existing CHP products worldwide and can provide combined efficiencies close to 90%. Molten carbonate and solid oxide fuel cells are also used for combined heat and power generation and have electrical energy efficiencies around 60%. Disadvantages of cogeneration systems include slow ramping up and down rates, high cost and short lifetime. Also, their need to have a hot water storage tank to smooth out the thermal heat production was a serious disadvantage in the domestic marketplace, where spacing domestic properties is at a great premium. Fuel cell electric vehicles. Automobiles. Although there are currently no fuel cell vehicles available for commercial sale, over 20 fuel cell electric vehicle prototypes and demonstration cars have been released since 2009. Demonstration models include the Honda FCX Clarity, Toyota FCH-VADV, and Mercedes-Benz F-Cell. As of June 2011, demonstration FCEVs had driven more than 4,800,000 km, with more than 27,000 refuelings. Demonstration fuel cell vehicles have been produced with a driving range of more than 400 km between refueling. They can be refueled in less than 5 minutes. The U.S. Department of Energy's Fuel Cell Technology Program claims that, as of 2011, fuel cells achieved 53.59% efficiency at 1/4 power and 42.53% vehicle efficiency at full power, and a durability of over 120,000 km with less than 10% degradation. In a well-to-wheels simulation analysis that did not address the economics and market constraints, General Motors and its partners estimated that per mile traveled, a fuel cell electric vehicle running on compressed gaseous hydrogen produced from natural gas could use about 40% less energy and emit 45% less greenhouse gases than an internal combustion vehicle. A lead engineer from the Department of Energy, whose team is testing fuel cell cars, said in 2011 that the potential appeal is that these are full-function vehicles with no limitations on range or refueling rate, so they are a direct replacement for any vehicle. For instance, if you drive a full-sized SUV and pull a boat up into the mountains, you can do that with this technology, and you can't with current battery-only vehicles, which are more geared towards city driving. Some experts believe, however, that fuel cell cars will never become economically competitive with other technologies, or that it will take decades for them to become profitable. In July 2011, the chairman and CEO of General Motors, Daniel Akerson, stated that while the cost of hydrogen fuel cell cars is decreasing, the car is still too expensive and probably won't be practical until the 2020-plus period. I don't know. In 2012, Lux Research, Incorporated issued a report that stated, "The dream of a hydrogen economy is no nearer." It concluded that capital cost will limit adoption to a mere 5.9 GW by 2030, providing a nearly insurmountable barrier to adoption, except in niche applications. The analysis concluded that, by 2030, PEM stationary market will reach $1 billion, while the vehicle market, including forklifts, will reach a total of $2 billion. Other analyses cite the lack of an extensive hydrogen infrastructure in the U.S. as an ongoing challenge to fuel cell electric vehicle commercialization. In 2006, a study for the IEEE showed that for hydrogen produced via electrolysis of water, only about 25% of the power generated from wind, water, or sun is converted to practical use. The study further noted that electricity obtained from hydrogen fuel cells appears to be 4 times as expensive as electricity drawn from the electrical transmission grid. Because of the high energy losses, hydrogen cannot compete with electricity. Furthermore, the study found, natural gas reforming is not a sustainable solution. The large amount of energy required to isolate hydrogen from natural compounds, package the light gas by compression or liquefaction, transfer the energy carrier to the user, plus the energy lost when it is converted to useful electricity with fuel cells, leaves around 25% for practical use. Despite this, several major car manufacturers have announced plans to introduce a production model of a fuel cell car in 2015. In 2013, Toyota has stated that it plans to introduce such a vehicle at a price of less than $100,000. Mercedes-Benz announced that they would move the scheduled production date of their fuel cell car from 2015 up to 2014, asserting that the product is ready for the market technically. The issue is infrastructure. At the Paris Auto Show in September 2012, Hyundai announced that it plans to begin producing a commercial production fuel cell model in December 2012 and hopes to deliver 1,000 of them by 2015. Other manufacturers planning to sell fuel cell electric vehicles commercially by 2016 or earlier include General Motors, Honda, and Nissan. The Obama administration sought to reduce funding for the development of fuel cell vehicles, concluding that other vehicle technologies will lead to quicker reduction in emissions in a shorter time. Stephen Chu, the United States Secretary of Energy, stated in 2009 that hydrogen vehicles will not be practical over the next 10 to 20 years. In 2012, however, Chu stated that he saw fuel cell cars as more economically feasible as natural gas prices have fallen and hydrogen reforming technologies have improved. Buses. As of August 2011, there were a total of approximately 100 fuel cell buses deployed around the world. Most buses are produced by UTC Power, Toyota, Ballard, Hydrogenics, and Proton Motor. UTC buses had accumulated over 970,000 km of driving by 2011. Fuel cell buses have a 141% higher fuel economy than diesel buses and natural gas buses. Fuel cell buses have been deployed around the world including in Whistler, Canada. San Francisco, United States. Hamburg, Germany. Shanghai, China. London, England. São Paulo, Brazil. As well as several others. The Fuel Cell Bus Club is a global cooperative effort in trial fuel cell buses. Notable projects include 12 fuel cell buses are being deployed in the Oakland and San Francisco Bay Area of California. Daimler AG, with 36 experimental buses powered by Ballard Power Systems fuel cells, completed a successful 3-year trial, in 11 cities, in January 2007. A fleet of Thor buses with UTC Power fuel cells was deployed in California, operated by Sunline Transit Agency. The first Brazilian hydrogen fuel cell bus prototype in Brazil was deployed in São Paulo. The bus was manufactured in Caxias do Sul and the hydrogen fuel will be produced in São Bernardo do Campo from water through electrolyses. The program, called Ônibus Brasileiro e Hidrogênio, includes 3 additional buses. Forklifts. A fuel cell forklift is a fuel cell-powered industrial forklift truck used to lift and transport materials. Most fuel cells used for material handling purposes are powered by PEM fuel cells. In 2013 there were over 4,000 fuel cell forklifts used in material handling in the USA, of which only 500 received funding from DOE. Fuel cell fleets are operated by a large number of companies, including Cisco Foods, FedEx Freight, GENCO, and HEB Grosses. Europe demonstrated 30 fuel cell forklifts with high lift and extended it with HY Lift Europe to 200 units, with other projects in France and Austria. Pike Research stated in 2011 that fuel cell-powered forklifts will be the largest driver of hydrogen fuel demand by 2020. PEM fuel cell-powered forklifts provide significant benefits over both petroleum and battery-powered forklifts as they produce no local emissions, can work for a full 8-hour shift on a single tank of hydrogen, can be refueled in 3 minutes and have a lifetime of 8 to 10 years. Fuel cell-powered forklifts are often used in refrigerated warehouses, as their performance is not degraded by lower temperatures. Many companies do not use petroleum-powered forklifts, as these vehicles work indoors where emissions must be controlled, and instead are turning to electric forklifts. In design, the FC units are often made as drop-in replacements. Motorcycles and bicycles. In 2005, a British manufacturer of hydrogen-powered fuel cells, Intelligent Energy, produced the first working hydrogen-run motorcycle called the ENV. The motorcycle holds enough fuel to run for 4 hours, and to travel 160 km in an urban area, at a top speed of 80 km per hour. In 2004, Honda developed a fuel cell motorcycle that utilized the Honda FC stack. Other examples of motorbikes and bicycles that use hydrogen fuel cells include the Taiwanese company APFCT's scooter using the fueling system from Italy's Actus Spa, and the Suzuki Bergman scooter with an IE fuel cell that received EU whole vehicle type approval in 2011. Suzuki Motor Corporation and IE have announced a joint venture to accelerate the commercialization of zero-emission vehicles. Airplanes. Boeing researchers and industry partners throughout Europe conducted experimental flight tests in February 2008 of a manned airplane powered only by a fuel cell and lightweight batteries. The fuel cell demonstrator airplane, as it was called, used a proton exchange membrane fuel cell lithium-ion battery hybrid system to power an electric motor, which was coupled to a conventional propeller. In 2003, the world's first propeller-driven airplane to be powered entirely by a fuel cell was flown. The fuel cell was a unique flat-stack TM stack design, which allowed the fuel cell to be integrated with the aerodynamic surfaces of the plane. There have been several fuel cell-powered unmanned aerial vehicles. A Horizon fuel cell UAV set the record distance flown for a small UAV in 2007. The military is especially interested in this application because of the low noise, low thermal signature and ability to attain high altitude. In 2009, the Naval Research Laboratory's Ion Tiger utilized a hydrogen-powered fuel cell and flew for 23 hours and 17 minutes. Fuel cells are also being used to provide auxiliary power in aircraft, replacing fossil fuel generators that were previously used to start the engines and power onboard electrical needs. Fuel cells can help airplanes reduce CO2 and other pollutant emissions and noise. Boats. The world's first fuel cell boat Hydra used an AFC system with 6.5 kW net output. Iceland has committed to converting its vast fishing fleet to use fuel cells to provide auxiliary power by 2015 and, eventually, to provide primary power in its boats. Amsterdam recently introduced its first fuel cell-powered boat that ferries people around the city's famous and beautiful canals. Submarines. The Type 212 submarines of the German and Italian navies use fuel cells to remain submerged for weeks without the need to surface. The U-212A is a non-nuclear submarine developed by German naval shipyard Volkswagen Deutsche WERFT. The system consists of 9 PEM fuel cells, providing between 30 kW and 50 kW each. The ship is silent, giving it an advantage in the detection of other submarines. Portable power systems. Portable power systems that use fuel cells can be used in the leisure sector, the industrial sector, and in the military sector. SFC Energy is a German manufacturer of direct methanol fuel cells for a variety of portable power systems. Enzel Systems Incorporated is an integrator of portable power systems, using the SFC Energy DMFC. Other applications, providing power for base stations or cell sites, distributed generation, emergency power systems are a type of fuel cell system, which may include lighting, generators and other apparatus, to provide backup resources in a crisis or when regular systems fail. They find users in a wide variety of settings from residential homes to hospitals, scientific laboratories, data centers, telecommunication equipment and modern naval ships. An uninterrupted power supply provides emergency power and, depending on the topology, provide line regulation as well to connected equipment by supplying power from a separate source when utility power is not available. Unlike a standby generator, It can provide instant protection from a momentary power interruption. Baseload power plants, solar hydrogen fuel cell water heating, hybrid vehicles, pairing the fuel cell with either an ICE or a battery. Notebook computers for applications where AC charging may not be readily available. Portable charging docks for small electronics. Smartphones, laptops and tablets. Small heating appliances, food preservation, achieved by exhausting the oxygen and automatically maintaining oxygen exhaustion in a shipping container, containing, for example, fresh fish. Breathalyzers, where the amount of voltage generated by a fuel cell is used to determine the concentration of fuel in the sample. Carbon monoxide detector, electrochemical sensor. Fueling stations. There were over 85 hydrogen refueling stations in the U.S. in 2010. As of June 2012, California had 23 hydrogen refueling stations in operation. Honda announced plans in March 2011 to open the first station that would generate hydrogen through solar-powered renewable electrolyses. South Carolina also has 2 hydrogen fueling stations, in Aiken and Columbia, SC. The University of South Carolina, a founding member of the South Carolina Hydrogen and Fuel Cell Alliance, received $12.5 million from the United States Department of Energy for its Future Fuels program. The first public hydrogen refueling station in Iceland was opened in Reykjavik in 2003. This station serves 3 buses built by Daimler Chrysler that are in service in the public transport net of Reykjavik. The station produces the hydrogen it needs by itself, with an electrolyzing unit, and does not need refilling. All that enters is electricity and water. Royal Dutch Shell is also a partner in the project. The station has no roof, in order to allow any leaked hydrogen to escape to the atmosphere. The current 14 stations nationwide in Germany are planned to be expanded to 50 by 2015 through its public-private partnership now GmbH. Japan also has a hydrogen highway, as part of the Japan Hydrogen Fuel Cell Project. 12 hydrogen fueling stations have been built in 11 cities in Japan, and additional hydrogen stations could potentially be operational by 2015. Canada, Sweden and Norway also have hydrogen highways being implemented. Markets and economics. In 2012, fuel cell industry revenues exceeded $1 billion market value worldwide, with Asian Pacific countries shipping more than 3/4 of the fuel cell systems worldwide. However, as of October 2013, no public company in the industry had yet become profitable. There were 140,000 fuel cell stacks shipped globally in 2010, up from 11,000 shipments in 2007, and from 2011 to 2012 worldwide fuel cell shipments had an annual growth rate of 85%. Tanaka Kikinzoku Kogyo KK expanded its production facilities for fuel cell catalysts in 2013 to meet anticipated demand as the Japanese ENE farm scheme expects to install 50,000 units in 2013 and the company is experiencing rapid market growth. Approximately 50% of fuel cell shipments in 2010 were stationary fuel cells, up from about a third in 2009, and the 4 dominant producers in the fuel cell industry were the United States, Germany, Japan and South Korea. The Department of Energy Solid-State Energy Conversion Alliance found that, as of January 2011, stationary fuel cells generated power at approximately $724 to $775 per kilowatt installed. In 2011, Bloom Energy, a major fuel cell supplier, said that its fuel cells generated power at €9.11 per kilowatt-hour, including the price of fuel, maintenance, and hardware. Industry groups predict that there are sufficient platinum resources for future demand, and in 2007, research at Brookhaven National Laboratory suggested that platinum could be replaced by a gold-palladium coating, which may be less susceptible to poisoning and thereby improve fuel cell lifetime. Another method would use iron and sulfur instead of platinum. This would lower the cost of a fuel cell. The concept was being developed by a coalition of the John Innes Center and the University of Milan Bicocca. PEDOT cathodes are immune to monoxide poisoning. Research and development, August 2005, Georgia Institute of Technology researchers use triazole to raise the operating temperature of PEM fuel cells from below 100 AA°C to over 125 AA°C, claiming this will require less carbon monoxide purification of the hydrogen fuel. 2008 Monash University, Melbourne uses PEDOT as a cathode. 2009 researchers at the University of Dayton, in Ohio, show that arrays of vertically grown carbon nanotubes could be used as the catalyst in fuel cells. 2009, Y Carbon began to develop a carbide-derived carbon-based ultracapacitor, which they hoped would lead to fuel cells with higher energy density. 2009, a nickel-blister phosphine-based catalyst for fuel cells is demonstrated. 2013, British firm ACAL Energy develops a fuel cell that it says runs for 10,000 hours in simulated driving conditions. It asserts that the cost of fuel cell construction can be reduced to $40 per kilowatt. See also. References. Further reading, Vielstick, W. A.L., ed. Handbook of Fuel Cells, Advances in Electrocatalysis, Materials, Diagnostics and Durability. Hoboken, John Wiley & Sons, Gregor Hughes. Fuel Cell Technology, a Euro Handbook. CRC Press, James Lamini. Andrew Dix. Fuel Cell Systems Explained. Hoboken, John Wiley & Sons, Subhash C. Singhal. Kevin Kendall. High-Temperature Solid Oxide Fuel Cells Fundamentals, Design and Applications. Elsevier Academic Press, Frano Barber. PEM Fuel Cells Theory and Practice. Elsevier Academic Press, EG&G Technical Services, Incorporated Fuel Cell Technology Handbook, 7th edition. U.S. Department of Energy, Matthew M. Mensch. Fuel Cell Engines. Hoboken, John Wiley & Sons, Incorporated, Noriko Heiko Belling. Fuel Cells, Current Technology Challenges and Future Research Needs. Elsevier Academic Press, External links, Fuel Cell Today, a Euro-market-based intelligence on the fuel cell industry, fuel starvation in a hydrogen fuel cell animation how a fuel cell works and applications, fuel cell origins, 1840 a Euro 1890, TC 105 IEC Technical Standard for Fuel Cells, EERE, Hydrogen, Fuel Cells and Infrastructure Technologies Program, Thermodynamics of Electrolysis of Water and Hydrogen Fuel Cells, 2002 Portable Power Applications of Fuel Cells, U.S. Fuel Cell Council, DeWitt POMIS Teaching and Learning Package Fuel Cells, Solar Hydrogen Fuel Cell Water Heating.